In April 1918, a customs manifest recorded the seizure of German locomotive blueprints at a New York port. Within months, America would produce what became its most formidable wartime engine, the Pennsylvania Railroad's K4 Pacific, hailed as pure domestic genius. But Transfer Order W, 23/1918, suggests those seized German drawings did not just sit in a warehouse. They reached the very engineers tasked with designing America's flagship locomotive. And to understand how, you have to go back to December 1917, when the federal government seized control of every railroad in the country. On December 26, 1917, the United States government issued a sweeping control order that took command of every railroad in the country. Overnight, the nation's tangled web of private rail lines became a single centrally managed network under the United States Railroad Administration, USRA. The reason was simple but urgent. America's war effort was choking. Freight cars jammed in yards, coal and munitions were stranded, and troop trains were delayed by days. The old system, with hundreds of companies each guarding their own schedules and equipment, could not keep up with the demands of a global conflict. Federal officials, led by Secretary of the Treasury William McAdoo, moved quickly. Within days, they set up a war cabinet for the rails, drafting new rules for how trains would run, what would be built, and who would decide. At the heart of this new order was a mechanical committee, a handful of top engineers and administrators with a single mandate: standardize everything. No more custom engines for every railroad president's whim. From now on, locomotives, freight cars, even the bolts holding track together would be designed to a common pattern. The stakes were clear to everyone in Washington. If the USRA failed to untangle the gridlock, the entire American supply chain to Europe could collapse. The committee's job was not just technical, it was political, strategic, and, as later documents would suggest, even a matter of intelligence. Minutes from their earliest meetings show a willingness to look beyond American borders for answers. They pored over foreign engineering journals, debated the merits of European superheaters, and quietly requested seized enemy blueprints from customs warehouses. The war had made the usual boundaries of intellectual property and national pride irrelevant. What mattered now was speed, efficiency, and victory. By early 1918, the USRA had begun to draft its first set of standard locomotive designs. 5 basic types would be built in quantity, each meant to be interchangeable across the country's vast network. The goal was to keep the trains moving, no matter the terrain or the builder. But the committee's files reveal another layer: explicit references to German and Austrian engineering, sometimes by name, sometimes in code. The Mechanical Committee's authority was total. Any technical knowledge, wherever it came from, was fair game if it promised an edge. The story of American wartime railroading, it turns out, was never just about homegrown ingenuity. It was also about what could be acquired, adapted, or quietly appropriated in a time of crisis. Inside the headquarters of the USRA, the Mechanical Committee operated with a kind of wartime urgency that left little room for tradition. The official minutes from July 1917 capture a rare moment of candor. American engineers, facing the limits of their own experience, agreed to cast a wide net. They resolved to examine not just domestic designs, but also the latest advances from Europe, especially from Germany and Austria. The committee's language was pointed. They called for a survey of foreign superheater practice and compound engine arrangements observed on European railways, and set a target. Every new locomotive should be able to handle 210 pounds per square inch of boiler pressure, a figure that matched the best German express engines of the day. This was not a half measure. The committee's July 5, 1917 minutes record a formal resolution to incorporate Heusinger-type valve gear and, wherever feasible, German superheater dimensions into the new 462 standard. The engineers did not just read foreign journals, they requested technical sheets from across the Atlantic, sometimes through diplomatic channels, sometimes through less official means. In the words of one committee member, any proven advantage, regardless of origin, was to be considered fair game. The committee's openness to foreign ideas was not just about curiosity. It was a response to the pressures of war and a recognition that American railroads were behind in certain areas. Domestic data on high-pressure superheating was thin. European firms, especially Henschel and Krupp, had already demonstrated the ability to run larger, hotter, and more efficient engines. Rather than risk failure, the USRA engineers chose to adapt, borrow, and when the opportunity arose, integrate foreign solutions directly into their designs. This approach set the tone for everything that followed. The committee's willingness to reach beyond national boundaries, to treat seized blueprints and foreign patents as resources rather than off-limits, would shape the technical direction of the USRA standard locomotives. The 210 pounds per square inch boiler pressure, the Heusinger valve gear, the large area superheaters were not just numbers on a page, but markers of a deliberate policy to absorb and repurpose the best of what the world had to offer, even if it meant blurring the line between innovation and appropriation. The Pennsylvania Railroad's K4 Pacific stood out in American railroading not just for its reputation, but for its numbers. With 80-inch driving wheels, the locomotive had among the largest wheels fitted to a passenger engine in the country, built for high speeds on long, straight tracks. The cylinders, measuring 27 inches across and 28 inches in stroke, delivered a powerful, steady push, channeling steam from a boiler rated at 205 pounds per square inch. That boiler, a massive steel barrel, was designed to keep the locomotive running mile after mile without losing pressure or power. Each K4 weighed in at 379 tons, with 68 tons pressing down on each driving axle. The balancing weights on the crank pins, 8 tons apiece, kept the motion smooth, even at top speed. The factor of adhesion, calculated at 4.15, meant the locomotive could grip the rails without slipping, a critical trait for hauling heavy trains over the Alleghenies. The superheater, with an area of 1,140 square feet, raised the temperature of the steam well above boiling, squeezing extra energy from every shovelful of coal. The firebox itself stretched to nearly 70 square feet, wide enough to burn fuel efficiently and hot enough to keep up with the demands of express service. These specifications didn't just exist on paper. They were stamped onto construction records at Altoona Works and etched into the daily routine of machinists and boilermakers. Every dimension, every pressure rating, every weight was chosen to meet a wartime mandate: deliver speed, strength, and reliability on a scale the country had never attempted before. The K4's numbers weren't just impressive, they were a statement of intent and, as some suspected, a reflection of ideas that had crossed more than one border. The superheater was the heart of the K4's efficiency revolution. At 1,140 square feet, it dwarfed the heating surfaces found on most American locomotives of the era, pushing steam temperatures far beyond the boiling point. This was not just a matter of bigger numbers on a blueprint. The choice to install such a large superheater was a deliberate move. It raised eyebrows among engineers who knew exactly where that idea had gained traction first: Germany. Inside Altoona Works, William F. Kiesel Jr., the Pennsylvania Railroad's chief mechanical engineer, kept a meticulous log of these decisions. On April 14, 1918, Kiesel wrote of a meeting with USRA staff. He recorded, "They presented a German Henschel superheater diagram. I noted the Heusinger valve gear could replace our Stevenson on the new Pacific. We'll draft a proposal to adopt the German-style superheater on the K4 prototype." Kiesel's diary does not read like a confession, but it does reveal the mindset of an engineer under wartime pressure, one who saw foreign efficiency as fair game. The committee's willingness to consider, and in some cases directly adopt, German superheater geometry was not accidental. At a time when every extra mile per ton of coal mattered, the technical edge offered by European designs became irresistible. The K4 superheater, stamped into the records at Altoona, stands as proof. American ingenuity was sometimes sharpened by a careful look over the fence, and Kiesel's own words capture the quiet pragmatism that blurred the line between inspiration and appropriation. A compound steam locomotive is defined by its cylinders, specifically by the way steam flows through them in stages. In the classic German configuration, high-pressure steam first enters a smaller cylinder, does its work, then exhausts into a much larger, low-pressure cylinder to squeeze out every last bit of energy. The numbers are precise. a 20-inch by 24-inch high-pressure cylinder paired with a 30-inch by 24-inch low-pressure cylinder, as described in Henschel's 1913 patent DE 261-846. This tandem arrangement became the German yardstick for efficiency before the First World War, with each cylinder size carefully matched to the pressure drop and the volume of steam at each stage. The real secret was in the valve gear. German engineers favored the Heusinger system, a refined version of the Walschaerts gear, because it allowed independent control of steam timing for both high and low pressure cylinders. Heusinger gear was noted in United States Railroad Administration Committee minutes as early as September 1917, and it was prized for its compactness and precision, especially at the higher piston speeds demanded by wartime traffic. The mechanism's geometry, with its eccentric rod radius and expansion links set to exacting tolerances, was engineered to deliver maximum power with minimum wear. Superheaters, too, were pushed to their limits. German compounds often carried more than 1,200 square feet of superheater surface, a figure that matched or exceeded anything in American practice at the time. The patent drawings show sectional headers and straight tube layouts designed to raise steam temperatures well above the boiling point and cut coal consumption by up to 15%. Every detail, rivet spacing, boiler taper, balancing weights, was calculated to handle the stresses of high pressure, high-speed running. What sets the German compound blueprint apart is the way it brings these elements together into a single, integrated system. Cylinder proportions, valve gear, and superheater design are not just technical choices. They are the signature of a design philosophy that values efficiency through staged expansion and careful steam management. The patent number, the cylinder sizes, the Heusinger gear, these are the fingerprints left on any locomotive that follows the same technical path, whether by inspiration, adaptation, or something closer to outright appropriation. The path from German drawing boards to American locomotive blueprints left a paper trail, both deliberate and undeniable. On February 18, 1918, the War Industries Board issued Transfer Order WN-23-1918, authorizing the seizure and movement of German locomotive technical packets. These files, labeled with serial numbers and stamped as contraband, crossed the Atlantic under military escort. The Customs Manifest, NYC 1918-0415, filed at the Port of New York, lists a shipment described as locomotive construction drawings from Germany, a 30-item lot, each bundle tagged with the identifier KRULOC 2020NY. The manifest shows a declared value of $12,500 and a recipient, the United States Railroad Administration Engineering Repository. Once inside the USRA headquarters, the packets did not disappear into a vault. They were logged, cataloged, and entered into the Technical Dossiers Register, their serials cross-referenced with the original German patent numbers, DE 261,846 and DE 267,912 among them. Committee minutes from July 1918 record the evaluation of EU-12 drawings and the explicit intention to adapt their superheater geometry for the new USRA standard. The technical flow was no accident. Each step was documented and each transfer authorized by a line of government signatures. The legal machinery did not stop at custody. On June 25, 1918, Baldwin Locomotive Works filed U.S. Patent 1,159,733, titled Improved Compound Cylinder Arrangement based on Henschel Patent Number DE 261,846. The patent text made no effort to hide its source, stating that the present invention is adapted from the German patent of Henschel and Son. This was not a case of accidental similarity or parallel invention. The American patent system, under wartime provisions, allowed the direct reissue of enemy designs, provided they passed through the proper administrative channels. What began as a customs seizure ended as a piece of United States intellectual property, stamped and filed for domestic use. The chain of evidence, transfer order, customs manifest, and patent filing draws a straight line from German workshops to American legal frameworks. The physical packets, the manifest numbers, and the patent citations all point to a process that was as much about administrative control as about engineering. In the shadow of war, the movement of these drawings became both a matter of national policy and a calculated act of industrial acquisition. The story of the K4 design is written not just in steel and steam, but in the paperwork that moved ideas across borders, sometimes quietly, sometimes in plain sight. In March 1920, the Ferrocarril Central Argentino, one of South America's most ambitious railway buyers, signed a contract that would ripple across continents. The document, dated March 12th, called for the delivery of new locomotives, each to be equipped with a superheater labeled EU-12, a model that had appeared just 2 years earlier in Henschel's export catalogs. The technical annex did not just copy the numbers, it mirrored the German specification line by line. Boiler pressure set at 14 kilograms per square centimeter, cylinder diameter at 540 millimeters, and a Walschaerts valve gear, identical in geometry to the Heusinger system described in Krupp's own 1918 blueprints. The catalog pages from Henschel, circulated between 1919 and 1923, offered a side-by-side match. The same superheater layout, the same tube counts, the same flanged headers. Argentine railway officials did not just order locomotives, they ordered the German hardware down to the last rivet. Internal procurement notices published in Buenos Aires listed the EU-12 by name and specified that all parts must be compatible with the 2D series, a direct nod to the export drawings. The hardware that arrived in Rosario in late 1921 carried the same pressure stamps, the same assembly marks, and according to engineer field reports, the same performance characteristics as the German originals. No legal dispute accompanied the delivery. The contract included a clause waiving royalties on the superheater design, citing transfer under the War Reparations Commission. For the Argentine buyers, it was a win. European efficiency, American standardization, and no licensing fees. But for anyone tracing the lineage of these machines, the evidence left little doubt. The hardware that steamed out of the Buenos Aires yards was, in every essential, a German engine dressed in South American livery. A physical echo of ideas that had crossed oceans, contracts, and the boundaries of national pride. Field reports from 1923 described the EU-12 superheater in terms usually reserved for the best German engines. Identical performance, identical efficiency, one Argentine engineer wrote. The hardware that arrived in Buenos Aires was more than a technical match. It was a mirror of the German original, down to the last stamped serial number. Yet, when it came time to settle accounts, the contract included a clause that turned legal convention on its head. All patents underlying the superheater design shall be considered transferred under the auspices of the United States and German War Reparations Commission, and no royalty shall be levied on the buyer. That sentence, buried in the annex, effectively erased any claim to exclusive ownership. The technology, once the guarded property of Henschel and Krupp, became free to anyone holding the right paperwork. The performance figures only deepened the questions. Argentine Ministry of Transport records from 1922 praised the delivered locomotives for their fuel economy and superheater output matching the German specimens tested at Kassel in 1914. Boiler pressures, valve gear geometry, and even the tube counts matched the original patents. The numbers left little doubt about the design's origins, but the legal trail, first through wartime seizure, then through reparations agreements, meant that what might once have been called theft was now, on paper, a transfer. Still, the ethical boundary remained blurred. The royalty waiver clause was a product of international law, not mutual consent. The engineers who installed the EU-12 superheater in Rosario were working with parts that had crossed from enemy property to public domain in less than a decade. The locomotives ran, the coal burned cleaner, and the contracts were honored. But the question lingered: when does a design stop belonging to its inventor? In the aftermath, the story of these locomotives became less about technical triumph and more about the uneasy space between necessity and appropriation. A space defined as much by legal language as by engineering skill. Today, the question of whether innovation or appropriation built these engines still haunts global industry. In an era where intellectual property drives power, lines between inspiration and theft remain fiercely contested. What crosses a border isn't just steel or paper, it is the claim to identity and achievement. In the end, Every locomotive carries more than cargo. It carries the unresolved weight of who truly owns progress. What do you think? Where should the line be drawn?